This week, our activities, content, and assignments will help you be able to do the following. 1. Learn about greenhouse gases and how they trap heat in the atmosphere. Observe the correlation of carbon dioxide concentrations and methane concentrations with variation in Earth's surface temperature. 3. Learn about glacial and interglacial periods. And 4. Explore the natural and anthropogenic causes of global warming. First, we'll start with some background information to provide you context for this week's lab. To understand climate change and paleoclimatology, we'll need to start with some background information. This includes terms, controls on Earth's climate, and scientific evidence. Let's review the distinctions between weather, climate, global warming, and climate change. Weather refers to the short term, minutes to weeks, state of the atmosphere at a specific time and place. It includes conditions such as temperature, humidity, precipitation, cloudiness, visibility, and wind. Weather is what you expect day to day and can change rapidly. For example, one day it might be sunny and warm, and the next day it could be rainy and cool. Climate, in contrast, is the average of weather conditions over longer periods, usually 30 years or more, in a specific area. It encompasses the regular patterns of weather measurements and their variability. For example, a region with a desert climate typically has a hot, dry weather with minimal rainfall, not just on a specific day, but over many years. Global warming specifically refers to the observed rise in Earth's average surface temperature. This trend has been particularly noticeable in the late 19th century due to human activities, predominantly the burning of fossil fuels like coal, oil, and natural gas, and deforestation. These activities increase concentrations of greenhouse gases in the atmosphere, enhancing the natural greenhouse effect and leading to a warming of Earth's surface. Climate change encompasses not only global warming, but also the broader range of changes happening to our planet. These include changes in precipitation patterns, increases in the frequency and severity of extreme weather events, sea level rise, melting glaciers, changes in ecosystems and wildlife patterns, and ocean acidification. Climate change considers both the direct increase in temperatures and the resulting alteration in Earth's environmental systems. Greenhouse gases are atmospheric gases that trap heat within the Earth's atmosphere. The most common greenhouse gases include carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, ozone, O3, and water vapor, H2O. Water vapor is the most potent greenhouse gas. However, carbon dioxide has the greatest combined potency and abundance. Carbon dioxide can come from volcanic activity, respiration of people and livestock, the decay of organic matter, and fossil fuel combustion. The greenhouse effect is a natural process that warms Earth's surface and is fundamental to maintaining the climate conditions necessary for life as we know it. It is primarily controlled by the presence of certain gases in Earth's atmosphere that can absorb and emit infrared radiation. The basic steps of the greenhouse effect are outlined here. 1. Incoming solar radiation travels through space and reaches Earth. Some of this solar radiation is absorbed by Earth's surface, causing it to warm. 2. Earth's surface reflects some of this energy back into the atmosphere as heat. Greenhouse gases in our atmosphere absorb and re-emit this infrared radiation, or heat, in all directions. 3. When greenhouse gases absorb the heat, they re-emit this energy in all directions, which traps most of it in our atmosphere, kind of like the glass in a greenhouse. It's important to remember that without the greenhouse effect, Earth's average surface temperature would be about -18 degrees Celsius or 0 degrees Fahrenheit, far too cold to support most current life forms. Instead, the average surface temperature is a much more hospitable, approximately 14 degrees Celsius or 57 degrees Fahrenheit. However, human-induced increases in greenhouse gases are amplifying this effect, leading to significant changes in climate patterns. Plate tectonics also influence Earth's climate over geologic timescales. This influence is exerted through several mechanisms. The configuration of continents and ocean basins, which changes as plates move, can significantly alter patterns of oceanic and atmospheric circulation. Plate tectonics is also responsible for volcanic activity. Volcanoes release large amounts of greenhouse gases, like carbon dioxide and water vapor, into the atmosphere. Over long timescales, increased volcanic activity can lead to warmer climates due to the enhanced greenhouse effect. Conversely, a decrease in volcanic activity can lead to a reduction in atmospheric greenhouse gases, potentially contributing to global cooling. The movement of ocean waters is driven by a combination of wind, Earth's rotation, the position of the continents, and differences in water density, which are influenced by temperature and salinity. Thermohaline circulation refers to the global conveyor belt of ocean currents, driven by differences in water density, which is affected by temperature, thermo, and salinity, haline. Cold, salty water is denser and sinks, while warmer, less salty water is lighter and rises. This creates a global system of deep water currents that circulate ocean waters worldwide. Milankovitch cycles, named after Serbian astrophysicist Milutin Milankovitch, are long-term changes in Earth's orbit and orientation in space that significantly influence Earth's climate over tens of thousands of years to hundreds of thousands of years. These cycles are a key factor in understanding past climate variations, such as the ice ages. There are three main components to Milankovitch cycles. The first is the axial precession, or the wobble. This is a gradual wobble in Earth's rotation axis. This cycle occurs over a period of about 26,000 years. Precession changes the timing of the seasons in relation to Earth's position and its orbit around the Sun. For instance, currently, Earth is closest to the Sun during the Northern Hemisphere's winter, but in about 13,000 years, this will occur during the Northern Hemisphere's summer. This shift can have substantial effects on climate, especially when combined with the other Milankovitch cycles. Next, we have obliquity. This is the angle of Earth's axial tilt with respect to its orbital plane. This tilt varies between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. A greater tilt means more extreme seasonal variations in climate, with warmer summers and colder winters, because the sun's rays strike Earth more directly in summer and less directly in the winter. Lower tilt results in milder seasons and can promote ice age conditions if summers are cool enough to prevent all the accumulated winter ice from melting. Finally, we have eccentricity. Eccentricity refers to the shape of Earth's orbit around the Sun. This orbit varies from being more circular to more elliptical in a cycle of about 100,000 years. When the orbit is more elliptical, there's a greater variation in the distance between Earth and Sun during the year, which affects the amount of solar energy Earth receives. This variation can influence the onset and end of ice ages. We are currently in the middle of a glacial period, although it's less intense now than it was 20,000 years ago. But this is not the only period of glaciation in Earth's history. There have been many in the distant past. In general, however, Earth has been warm enough to be ice-free for much more of the time than it has been cold enough to be glaciated. This diagram shows the past 500,000 years of the same data set shown here. The last 5 glacial periods are marked with snowflakes. The most recent one, which peaked at around 20,000 years, was known as the Wisconsin glaciation. Describe the nature of temperature change that followed each of these glacial periods. The current interglacial period is marked with an H. These variations are attributed to subtle changes in Earth's orbital parameters, or Milankovitch cycles. Over the past million years, the glaciation cycles have been approximately 100,000 years apart. Finally, humans exert a large control on Earth's atmosphere through land use changes, including deforestation and agriculture, and the burning of fossil fuels. Our planet is hotter than it has been for thousands of years, and the pace of warming is accelerating. This graph is showing the temperature anomaly, the global temperature anomaly, which refers to the deviation of Earth's surface temperature from a specific range or value, or a long-term average. It is a key metric used in climate science to assess changes in Earth's climate. One of the most direct indicators of climate change is the measured increase in global surface temperatures. Decades of temperature data show a clear warming trend, with recent years being the warmest on record. This trend is consistent across land and ocean temperature measurements. The Keeling curve is a graph that represents the concentration of carbon dioxide in Earth's atmosphere over time. This is named after Dr. Charles David Keeling, who initiated these measurements in 1958. The Keeling curve provides the longest continuous record of atmospheric carbon dioxide concentrations available. The most important thing to note here is the clear upward trend in carbon dioxide levels over time. When Dr. Keeling began his measurements in 1958, the atmospheric carbon dioxide concentration stood at approximately 315 parts per million, or ppm. Since then, it has risen steadily, surpassing 400 ppm in 2013, and continues to rise. This rise is directly linked to human activities, particularly the burning of fossil fuels, deforestation, and other land use changes. The Keeling curve shows a regular pattern of seasonal fluctuations in carbon dioxide levels. Each year, carbon dioxide concentrations rise during the northern hemisphere's fall and winter, and then fall during the spring and summer. This is because the northern hemisphere has the largest land mass with extensive vegetation. During the growth season, plants absorb carbon dioxide for photosynthesis, reducing atmospheric carbon dioxide levels. In the fall and winter, when plants decay or go dormant, carbon dioxide is released back into the atmosphere. Carbon emissions have been rising since the Industrial Revolution. This graph shows carbon dioxide emissions from fossil fuels and industry. So far, each of these three graphs that we've seen show the same trend, suggesting that humans are the cause of our changing climate. However, we have even more evidence showing that humans caused climate change. Paleoclimatology is considered the study of Earth's past climate through time by using different proxy records and archives. Examples of different types of records that can be used include ice cores, sediment cores, corals, tree rings, pollen records, historical records, and satellite data. Different types of records are better for bringing in different types of data or data over different time periods. For example, ocean sediments reach much further into the past than tree rings do. Specifically in this lab, we're looking at data from ice cores. Ice cores provide scientists with a way to learn about the environmental conditions in the past before people were around to write records. When snow falls on a glacier each year, creating a new layer of snow, as time passes, more layers are created, one each year. This results in a layer cake of snow. The weight of the snow at the top of the glacier starts to compress the snow below. This ultimately results in a layer cake of ice. We see different mini layers from summer and winter seasons as the seasonal variation in precipitation causes a different amount of dust to settle into the yearly snowfall. The benefit of drilling ice cores is that the core can be taken back to the laboratory to analyze, and since a new layer is created each year, the more layers that scientists can observe, the more years into the past they can investigate. The layers of ice provide information about the amount of snow that the glacier received each year. A thicker layer means that the glacier received more snow. A thinner layer means that the glacier received less snow. The layer of ice also contains materials such as debris from forest fires and volcanoes, and living materials such as pollen and insects. Many of these materials can be seen with the naked eye. More sophisticated techniques are used to analyze the amounts of these materials. A few examples include oxygen isotope ratios, dust concentrations, and sulfate concentrations. Oxygen isotope ratios, the ratio between oxygen 16 and oxygen 18, provide us with information about the temperature when the snow fell. Generally, a greater amount of oxygen 18 means a warmer atmosphere, and a lesser concentration of oxygen 18 means a colder environment. Scientists use bubbles trapped within the ice to analyze different isotopes trapped within the ice core, including oxygen, but also many others, like carbon. In the lab today, you will be looking at carbon dioxide and methane data from the Vostok ice core collected in Antarctica. We will consider the greenhouse gases a good correlation between past climate and temperature. One of the most important tasks scientists work on through paleoclimate is understanding the past so they can better predict the future. In this image from Heidi Roop of NSF, or the National Science Foundation, you can see a dark band in this ice core. This core is from the West Antarctic ice sheet divide, and the dark band is a layer of volcanic ash that settled into the ice sheet approximately 21,000 years ago. As a reminder, isotopes are atoms with the same number of protons but a different number of neutrons, which causes them to have a different mass and thus behave slightly differently. Unlike carbon-14, the amount of carbon-13 or carbon-12 in an artifact does not change over time, since both carbon-13 and carbon-12 are stable isotopes. In other words, they do not decay. Because they are stable isotopes, a carbon-13 atom will always remain a carbon-13 atom, and the same is true for carbon-12. Almost 99% of all carbon atoms are carbon-12. Even so, different carbon sources have different ratios of carbon-13 and carbon-12, called isotopic fingerprints. The differences are small. One carbon pool may have a 98.8% carbon-12 composition, while the other might have a 99.2% carbon-12 composition. But modern machines, called isotope ratio mass spectrometers, can detect these differences easily. Plants preferentially absorb more of the lighter carbon-12 during photosynthesis, making their carbon ratio different from that of the atmosphere. Because fossil fuels are formed from the remains of ancient plant material, they have a lower ratio of carbon-13 to carbon-12. As humans burn fossil fuels, such as coal, oil, and natural gas, the concentration of carbon dioxide in the atmosphere increases. When these fossil fuels are burned, they release carbon dioxide that has a low ratio of carbon-13 to carbon-12 relative to the atmospheric average. Therefore, the increasing concentration of carbon dioxide in the atmosphere, with that lower ratio of carbon-13 to carbon-12, is a strong indicator that the additional carbon dioxide is largely coming from the burning of fossil fuels. Now we'll discuss the consequences of climate change. Specifically, global effects of climate change in Ohio, and positive feedback loops. Although climate change is natural, the planet has been much hotter and much colder. It's the rate this time that's dangerous because ecosystems don't have time to adjust. We're in the sixth major extinction, which is proceeding at an unprecedented rate, even faster than the extinction event that killed the non-avian dinosaurs 66 million years ago. Humans will be impacted as well, not just our environment. The most impacted will be the least at fault and the least capable of adapting. Glacial retreat, a striking consequence of climate change, is the process where glaciers shrink and reduce in area due to melting ice, a phenomenon increasingly observed worldwide. Driven by rising global temperatures, this retreat has accelerated notably in recent decades. As glaciers melt, they contribute to rising sea levels, posing a threat to coastal communities. The loss of glaciers also impacts freshwater supplies. Many rivers and lakes are fed by glacial meltwater, which is crucial for ecosystems, agriculture, and human consumption. Furthermore, glacial retreat alters landscapes, affecting local ecosystems and potentially triggering natural hazards like landslides and glacial lake outburst floods. The retreat of these ice giants serves as a visible and alarming indicator of the ongoing changes in our planet's climate system. Another consequence of rising temperatures is the loss of sea ice. Since 1975, we've seen a loss in approximately 3 million cubic kilometers of sea ice in the Arctic. Rising sea levels are driven by two main processes. One, ice melt. When the atmosphere and the ocean get warmer, ice sheets and glaciers melt, resulting in the addition of fresh water to the ocean. Two, thermal expansion. As ocean water gets warmer, it expands, causing sea levels to rise. One of the most noticeable effects of climate change is the changing of Earth's sea levels. While most people understand that the ocean is vast and contains a lot of water, many fail to realize how little of a rise in sea level it would take before the relocation of coastal cities becomes a major concern. According to a University of Arizona study, a 1 meter or 3.28 feet rise in sea level would submerge parts of the Gulf area and South Atlantic coasts. But at 6 meters or almost 20 feet, 90% of Miami, New Orleans, and Virginia Beach would be underwater. The difference between a glacial period and an interglacial period of sea level is approximately 120 meters, or about 394 feet. While we are currently in an interglacial period, there is still plenty of room for the sea level to continue rising. Changing climates and habitats are leading to shifts in species, distributions, and ecosystems, which can result in the loss of biodiversity. Some species may become extinct if they cannot adapt or migrate, and new patterns of pests and diseases can emerge. One example of this is coral bleaching. Corals have a symbiotic relationship with microscopic algae called zooxanthellae that live in their tissues. These algae are the coral's primary food source and give them their color. When the symbiotic relationship becomes stressed due to increased ocean temperatures or pollution, the algae leave the coral's tissue. Without the algae, the coral loses a major source of food, turns white or very pale, and is more susceptible to disease. If the conditions aren't reversed, the coral will starve to death. Excess carbon dioxide is absorbed by the oceans, forming carbonic acid. This carbonic acid lowers the pH of seawater in a process known as ocean acidification. This increased acidity can harm marine organisms, particularly those with calcium carbonate shells or skeletons, like corals and some shellfish. This graph shows a decrease in the annual average pH of seawater over the last 35 years. Like we saw in the Keeling curve before, the carbon dioxide uptake is seasonal and is reflected in the average seawater pH. As global temperatures rise, Earth's weather systems become more volatile and unpredictable, leading to more extreme and destructive events. We've seen an increase in both frequency and severity of severe storms, hurricanes, droughts, floods, wildfires, and heat waves. Natural disasters not only cause immediate destruction and loss of life, but also carry long-term economic and social costs, disproportionately affecting the most vulnerable communities. In this graph, we see an increase in reported natural disasters. While we do know that we are experiencing increased disaster events, it's important to note that this sharp rise in the graph can partially be attributed to increases in data reporting. Ohio will experience many of the same effects seen in other areas of the globe. Specifically, Ohio has seen large increases in heavy storms that can lead to flooding. Models predict that those trends will continue, increasing flood damage risks to infrastructure and public health. The ice-free season along the Great Lakes is also becoming longer. Warmer water tends to cause more algal blooms, which can be unsightly, harm fish, and degrade water quality. Changing the climate will have both beneficial and harmful effects on farming. Longer frost-free growing seasons and higher concentrations of atmospheric carbon dioxide would increase yields for some crops during an average year. But increasingly hot summers are likely to reduce yields of corn and possibly soybeans in the longer term. Air quality deteriorates with warmer temperatures, increasing the risk of serious public health consequences. A greater incidence of asthma attacks and other respiratory conditions is also anticipated. Additionally, we have this figure over here to the right, showing how summer in Ohio and winter in Ohio are likely to change under different climate change scenarios. By 2030, Ohio will experience winters similar to that of West Virginia, and by 2095, Ohio will experience winters similar to that of North Carolina and Virginia. Summers, on the other hand, are going to get hotter and drier, like that we see in Illinois and even Arkansas. Positive feedback loops in the context of climate change are processes that amplify or accelerate a change in the climate system. When an initial change in the system leads to effects that further enhance that change, it creates a loop of self-reinforcing actions. This is opposed to negative feedback loops, which work to dampen or reduce the effects of a change. Several key positive feedback loops are particularly relevant in the discussion of climate change. The first is water evaporating. Water vapor, like we talked about earlier, is the most potent greenhouse gas. As temperatures rise, more water vapor evaporates from Earth's surface, increasing the amount of water vapor in the atmosphere. Since water vapor itself is a greenhouse gas, adding more to the atmosphere intensifies the greenhouse effect, leading to further warming. This warming causes more evaporation, and the cycle continues. Ice melting. Ice reflects a significant portion of solar radiation back into space. As global temperatures rise, ice, particularly in the Arctic and Antarctic regions, as well as mountain glaciers, melts, reducing Earth's reflectivity. The newly exposed surfaces, such as ocean water and land, have a lower reflectivity and absorb more solar radiation. This additional absorption of heat leads to further warming and more ice melt, creating a self-reinforcing loop. Permafrost thawing. Permafrost is permanently frozen ground found in polar regions. It contains large amounts of organic material. Arctic soil holds an estimated 1,460 to 1,600 billion tons of trapped carbon. This is almost twice the amount of the greenhouse gases currently in our atmosphere. When thawed, due to rising temperatures, this carbon starts to decompose. The decomposition process releases greenhouse gases like methane and carbon dioxide, which further contribute to the warming of the atmosphere. This warming then leads to more permafrost thawing, releasing even more greenhouse gases. Now we'll discuss something a little bit more uplifting: how to mitigate the consequences of climate change. Specifically, we'll take a look at current climate projections and examine available technology and personal and systemic changes that we can make to mitigate the effects of climate change. Temperatures will continue to rise because of greenhouse gases that are already in the atmosphere, and the problems that we are already experiencing are likely to worsen. But what's the good news? If we are able to curb emissions now, that could help us maintain a 1.5 degrees Celsius increase in temperature. However, if we surpass that 1.5 degrees Celsius benchmark, we could see even more severe consequences. And you may wonder, what's the difference between 1.5 degrees and 2 degrees? That's only 0.5 degrees difference. Well, that extra 0.5 degree difference could result in a 19% loss in corals, with only 1% of corals able to survive. It could result in doubling the percentage of total species lost, and it also could result in 30% more people in cities being severely impacted by drought, and roughly 3 million more people could be displaced because of rising sea levels. Technology plays an important role in both mitigation and removal of greenhouse gases. First, to reduce fossil fuel dependency, advancements in renewable energy technologies, such as solar, wind, and hydroelectric power, must be made. These sustainable alternatives not only decrease our carbon footprint, but they also offer long-term economic benefits. At the same time, improving energy efficiency across industries and households can substantially lower energy consumption. We can also remove carbon from the atmosphere through innovative solutions like carbon sequestration, where carbon dioxide is captured and stored in rocks underground. Replanting forests and improving agricultural practices removes carbon dioxide and enhances biodiversity and soil health. Additionally, the cultivation of algae offers two benefits. One, it absorbs carbon dioxide, and two, it can be used as a biofuel. There are two types of changes that we'll need to make in order to effectively address climate change. The first is systemic change. This means changes in systems and environments that address the underlying causes of climate change. Examples of this including participating or voting in elections, particularly local elections, petitioning your community to use solar, wind, bioenergy, calling your representatives, protesting, getting your friends, family, and local businesses involved, and joining climate justice organizations. The second is personal change. This means that you can changes that you can make in your own behavior to address climate change and reduce greenhouse gas emissions. Examples of this include using less water, energy, plastic, buying used whenever possible, recycling, growing your own food, and if possible, using renewables on your own, like using solar panels or collecting rainwater. If you're interested in participating and getting involved in climate change mitigation efforts, you can take additional courses in the School of Earth Sciences. The School of Environment and Natural Resources and the Department of Geography also have relevant courses. Additionally, you can participate in undergraduate research related to climate change and volunteer or join any of the listed organizations. Next, we'll discuss information that you'll need to complete this lab. There are no safety concerns specific to this lab. Helpful hints. Make sure you're paying attention when you're using Excel to which tab you are in, carbon dioxide or methane. Clicking on the data points themselves will help you to answer the questions. And finally, make sure you fill out your SEIs. This is really important for your TA's career. When they go to apply for different teaching jobs, it is immensely helpful if they have reviews from students like you.